In this video, I'm going to review the trigonometry necessary to succeed in physics. This is just going to be the basics of trigonometry, and let's get right into it. So in physics, you might draw thousands of free body diagrams. And in those free body diagrams, we're going to have forces going in the y direction, the x direction, and on the x and y here, like F1. And those forces that are on x and y are going to have components. So let's look at F1 here. If we have a force F1 moving upwards diagonally, we know that it moves some in the x direction and it moves some in the y direction. So we then say that F1 has an x and a y component. Now, in physics, that's very important because sometimes we know things about the x direction, we know things about the y direction, but we don't know things about F1. So in order to find F1, we need its components. And to find its components, we use basic trigonometry. So now that I've given you a short introduction, let's look at something you might do with your free body diagram. So this says break F1 into components and write out expressions for F1, Fy, and Fx. Fy is F1's y component, and Fx is F1's x component. So in order to do this, we need to review SOH CAH TOA. SOH CAH TOA refers to the acronym that describes the three main trig functions. And it also describes how to use them. So recall that these functions are useful when dealing with right-angled triangles. Just like F1 up here is a right-angled triangle. So recall that a right-angled triangle is a triangle, so it has three sides. It has two angles and then one right angle. Now, also recall that we use theta to represent an unknown angle. Just like x, theta is a variable. It's not some concrete number, it's just represents a location where we don't know an angle. So let's put theta in the left corner of this right-angled triangle. We also have to recall the side lengths of a right-angled triangle. This long diagonal is referred to as the hypotenuse. So we can denote that with h, but I'm going to write HYP for hypotenuse. Next, the other two side lengths have to do with the orientation of theta. So since theta is in the bottom left corner, its opposite is on the other side of the right angle triangle. So OPP for opposite. Now, adjacent is the last side, and obviously it's the only missing side, but it is because it's right beside theta, and that's why we call it adjacent. It's a good way to remember. Let me get rid of that arrow. So, if theta were in this corner, things would change. Let's say we're trying to find that angle, right? Adjacent would now be beside theta, where opposite is for the other theta, and opposite would now be across from theta, right? It depends on the orientation of theta, but the hypotenuse stays the same. It's just the long diagonal of your right-angled triangle. Next, we need to know what SOH CAH TOA really means. We need to recall all three of the basic trig functions. So let's start with SOH, and the S in SOH refers to sine. And we say sine of theta is equal to opposite divided by hypotenuse. Now, same thing with CA and TOA. CA is just the cosine of theta, and that's equal to the adjacent over hypotenuse, and T is the tangent of theta, which we say is the opposite over adjacent. Now, that's how you solve for side lengths, but let's say we need an angle. Because if we use one of these trig functions and we do O divided by H, whatever these values are, we just get the magnitude of sine theta. We don't really get the angle that it's on. So how are we going to solve for the angle? So let's start with sine theta. They're all the same, but we'll use sine theta as an example. So here's sine theta. And we know sine is opposite over hypotenuse, right? It's SOA. Sorry, it's SO in the SOH CAH TOA. So given this right angle triangle, we want to find angle theta. And I'm going to give you some side lengths to do that. So first, let's label what the opposite is. What is opposite to theta? Right, on the other side of the triangle, directly across from theta, not beside it. And let's label that as 6 meters per second. Let's say that this right-angled triangle is actually the trajectory of some velocity. And 6 meters per second is actually its y component. And we have to give it an x component and an hypotenuse. So the magnitude of this velocity, we'll say it's 10 meters per second. So that means the hypotenuse would be 10 meters per second. And you can use Pythagorean theorem to figure out the missing value of the side length here, but we are just going to find the angle. So how do we find this angle? If we just do 6 divided by 10, opposite over adjacent, that doesn't really give us an angle, right? That just gives us the value of sine theta. And that's why we must solve for theta. So theta is equal to sine inverse of opposite over adjacent. Now, on your calculator, you should see your sine function, and if you press shift, or a second function, the second function or shifted function on your calculator should be sine with a -1 on it. And that's just saying the inverse. And that's how you find the angle. That's how you get this theta out of the sine function and solve for it. Same thing for cosine, same thing for tangent. You would do its inverse and then the formula. So on your calculator, type in, I'm going to write it out first, but I want to show you how to do it on your calculator. So theta of sine inverse here is opposite, so 6 over 10. So on your calculator, you would do 6 divided by 10. That's it. Now you have 0.6, right? Then you would press second function or shift, and then press the inverse sine button. And that gives you the angle for the opposite and the hypotenuse being theta in this case. Now we could also find this angle using cosine, and I'll show you that in a second. So you should get 36.86, I didn't round anything, degrees. So what if we wanted to find that same angle with cosine? Well, I can't just move the 6 meters per second down to the adjacent side. We would actually get this angle. So how are we going to do this? If you recall Pythagorean theorem, a squared plus b squared is equal to c squared. So our unknown is a. So we're going to say a squared plus, and then b is our other side length, so 6 squared. And then c, remember, is always the hypotenuse, so 10 squared. And the hypotenuse is the long diagonal of the right angle triangle. So let's solve for a now. So a squared is equal to 100, because 10 squared, and then minus 36. So a squared is equal to 64. And then you would do square root both sides, get rid of that squared. And sorry, we're just going to scroll down here, let's zoom in. And then a is going to equal to the square root of 64, which is 8. So we got that a is equal to 8 meters per second using Pythagorean theorem. So 8 meters per second. So now the adjacent value for theta is, the adjacent side length for theta is equal to 8 meters per second. So let's find the same angle, 36.86, using cosine. So now let's find the same angle, 36.86, using cosine. So we know the cosine of theta is equal to ca, right? Remember, ca is adjacent over hypotenuse. So we have adjacent over hypotenuse. And that we solve for theta here, we get the inverse of cosine of adjacent hypotenuse. And that is the inverse cosine of what's adjacent? 8 there, divided by 10. So we should get 36.86, the same angle, but using a different function, using a different side length. So do 8 divided by 10 in your calculator, and then press second function, and then press inverse cos, then equals. Look at that, 36.86. And that's how trigonometry is used in physics. We get, if we're given some velocity vector that is 10 meters per second, and we're given that it's in like the x and y axis, we get the components using trigonometry, and then we could find the angle that it's at, and then, of course, the direction. So knowing all of this, knowing the basic trig functions, SOH CAH TOA, and how do you do it on your calculator, we can now go back to the original problem. Okay, so now we're back to our original problem, and we're armed with everything we need to solve it. So break F1 into components and write out expressions for F1, Fy, and Fx. Well, we just did SOH CAH TOA and the Pythagorean theorem. So how are we going to break it into components? So let's isolate F1. What does F1 look like on a right angle triangle? It looks like the hypotenuse, right? And then fx, I keep saying f of x. Fx is the x component of F1, and that is along the x-axis. And Fy is along the y-axis, and that's the y component of F1. So how do we write an expression for this? So F1, we could write an expression for no problem, because we know the Pythagorean theorem is a squared plus b squared equals to c squared, right? And this being the hypotenuse and also c in our formula, we can just easily do that, right? So let's write an expression for F1. So using a squared plus b squared equals to c squared, we know that fx squared plus fy squared is equal to F1 squared. This is how we find magnitudes for our vectors. So now solving for F1, you take the square root of both sides, and you get this F1 is equal to the square root of fx plus fy. That's it. That's your expression for F1. Now let's do it for Fy and Fx. And I'll give you a hint, it has nothing to do with Pythagorean theorem. It has everything to do with SOH CAH TOA. So, Fx is equal to what? Recall there's an angle right here. Where's f of x? Where is fx relative to that angle? It's adjacent, right? So given that it's adjacent, and we have f1 here to use, we're definitely going to use sine. Definitely. Sorry, cosine, because it's adjacent. And remember, SOH CAH TOA, cosine is adjacent over hypotenuse. So to do this, we need the magnitude of f1, cosine of theta. And that is our component fx. Now for fy, we know that it's opposite, so we're definitely using sine, because opposite over hypotenuse, so we get the magnitude of f1 times the sine of theta. And you might be confused because our triangle, when we did the right angle triangle, we had something that looked like this, right? Sine of theta is equal to opposite over hypotenuse. And this is looking a little different. But if we just solve for opposite, then it looks pretty similar, right? Opposite is equal to h times the hypotenuse times sine of theta, right? So let's go back to our components here. So we have sine theta. What is the opposite of sine theta? It's fy, right? Across from it. So let's put fy there. And the hypotenuse, of course, is f1, the magnitude of f1. So we want to write an expression for fy. So let's solve for fy. So multiply f1 on both sides, and we get f1 sine of theta is equal to fy. And there's your expression for fy. And you can do the same thing with fx. Now, here's a bonus question. Write an expression for theta. Write an expression for theta. How would you do that? Using these components. Well, you can do it many ways. We remember how we said, like, you can just do the inverse cos, but you should remember that if you don't have f1, you can use these components. So the inverse tan of opposite over adjacent is theta. So theta is equal to tan inverse of opposite fy over fx. And that is all you need to know for physics with trig. You could benefit from knowing the law of parallelograms and the sine law and the cosine law, but to be honest, you rarely use it, and you mostly just find the angles like this. But I'm going to make a video on the sine law and the cosine law, so if you need that, be sure to watch that. I hope you enjoyed this video. Thank you for watching. Subscribe if you want more content from me. Don't subscribe if you hated this video. Please tell me how bad it was, because I don't have a lot of videos out, and I just want to know what I'm doing wrong, what I'm doing right. So have a great rest of your day. Watch some more of my content, please.